This is my ball balancing robot. In this video, I will show you how I made this robot and how you might want to make yours. The robot uses a camera and OpenCV to track the ball. Then it uses a PID algorithm and inverse kinematics to control the servos and manipulate the top platform to balance the ball. To build this robot, I would need a sensor that is capable of accurately tracking the ball's position. Next, I need an algorithm that can take the coordinates of the ball and convert them into a PWM signal to control the servos. Finally, I need a platform for the servos to control. This platform must be able to tilt in any direction and balance the ball. Sounds simple enough, right? Wrong. It took me a year to build this robot, so please enjoy this video. Now, I need to pick the hardware. A wide-angle camera would be best to track the position of the ball. I tried using a regular Pi camera, but it could not see the entire platform. Next, I need to pick the brains of the robot. Since I wanted to use camera-based object detection that is too complex for an Arduino or ESP32, I chose the Raspberry Pi 4B instead. And finally, I need to pick the arms. I'm using 20 kilogram servo motors since they're easy to control and very powerful. With all the parts picked, it was time for CAD. I designed the robot in Onshape. I already learned CAD from past projects, but this was a real test of my skills and a huge learning experience. In the beginning, I underestimated how robust the design had to be, but slowly, after many failed prints, I revised it until the robot was able to work. The biggest thing I learned was not to try and print everything. For example, in the beginning, I wanted to print the hinge and the spherical joint, but this was just way too weak and unreliable. I also learned to make everything stiffer and stronger than it needs to be. This is also a good time to talk about powering issues I had. One problem I had was that the servos would jitter and move around randomly because I was using a weak 5-volt USB power supply. So I switched to an adjustable power supply that could reach up to 12 amps. This worked much better. Another problem I had was that I didn't know I had to connect the ground of the power supply to the Raspberry Pi's ground. This caused me to be stuck for a long time since I couldn't figure out why the servos weren't responding. And the final problem was that I sucked at soldering, so many times I had to re-solder the connections. Over time, I got better at soldering and I fixed all my issues. Next, I used OpenCV to detect the ball. OpenCV has many useful functions such as the HSV filter and the rotating and dilating. I used an HSV filter to filter out everything except the ball. Splitting the HSV channels is super useful for finding a good range. The HSV filter basically works by only allowing the parts of the camera stream inside the HSV range to pass. This is shown in white. Next, I used a small dilate, then a larger rode, and finally a larger dilate. This first fills the gaps in the ball, then it removes all the tiny dots of unwanted noise, and finally it increases the size of the ball to make it easier to detect. Now it is time for inverse kinematics. Inverse kinematics is basically just a lot of math to calculate the angle the servos should be set to for the platform to reach a certain position and angle. I definitely did not want to derive the equations by myself, so I followed George Wong's explanation. Going through the inverse kinematics was really useful for me to understand the project more, and I really recommend you trying inverse kinematics. Solving the inverse kinematics also helped me figure out a major issue I didn't realize, which was that the way I calculated the PID was wrong since I did not allow negative values. I will explain more on this later. And now for PID tuning. The PID algorithm calculates how much we should tilt the platform. Imagine the ball is moving away from the platform very fast. Then we would need to tilt quickly in the opposite direction to slow the ball down. Or if the ball is very close to the center and not moving at all, we should only tilt it a little bit towards the center. This is what a PID algorithm calculates. Now, given these ball coordinates, how would you calculate the error? If you did something like the distance formula, that's wrong. This is because the error has to be able to be negative. The correct way to split the x and y errors is actually to calculate it like this: center x minus ball x, and center y minus ball y. Then we can combine the two and plug them into the inverse kinematics function. PID tuning was the least enjoyable part of this whole project for me. Almost all of the tutorials I found used the graph to tune the PID, but I did not have a graph in my robot. It would have been possible to store all the x and y values and plot a graph, but there are two main reasons why I didn't do this. First, the increased code and calculations would reduce the FPS, making it harder for the robot to balance the ball. And the PID graph wouldn't even represent the real PID loop because of the added lag. The second reason is that if a ball reaches a certain position on my robot, it'll just fall off, so the graph would be cut off and not very helpful. I was able to find common patterns in PID tuning, such as an unstable PID loop and a sustained oscillation PID loop. This helped me determine how I should adjust the values, which is really helpful. But in order to understand how you should adjust the values, you need to understand what each of the P, I, and D do. So I'm going to quickly go over what each of these do. The P stands for proportional, and it is proportional to the error. So if the ball is far away from the center, it tilts a lot, and if it is close to the center, it only tilts a little. However, this by itself cannot balance the ball. For me, the P term was always enough to perfectly make the ball fall off. This is why we need the D term. The D term is calculated by the slope of the error, and it's supposed to dampen the P term. So if the ball is moving very quickly towards the center, the D term will try to slow the ball down by tilting in the opposite direction. This sounds great, but in practice, the D term is very hard to use. One problem is noisy data. Since the term is calculated by the slope, noisy data can make it very unreliable. Another issue is that the D term relies on time, and if the time isn't steady enough, then the slope will also be messed up. So having an inconsistent time loop will make the D term pretty unreliable. This is why I also use the V term. It's called the V term because it's calculated from the velocity. The V term dampens the effect of the P term, except it's more reliable than the D term. I also multiplied the V term by the error to the power of 0.65 so that it would have a greater effect near the sides and less effect near the center. This will keep the system stable while being able to save faster moving balls. And that's everything I did to build this ball balancing robot. If you liked the video, please subscribe.